Welcome to This Explainer. Today, we are uncovering the fundamental magic of mapping space. We're going to explore exactly how we take our messy, physical, three-dimensional world and translate it into the incredibly precise, beautiful language of mathematics.
Okay, let's kick things off with a question I think we can all relate to. How do you accurately describe the exact location of anything? It's a literal puzzle that humans have been trying to solve for thousands of years. Whether it's finding a specific shop in an ancient city, guiding a massive ship across the ocean, or simply, helping someone navigate their own bedroom.
Here is our roadmap for the explainer today. 1. The room on a grid. 2. The 2D Cartesian system. 3. Understanding the 4 quadrants. 4. Plotting points and distances. And 5. History of coordinate geometry. Let's jump right in.
Section 1. The room on a grid. We're going to begin our journey moving from the concrete to the abstract, starting with a story about a student named Rian who is moving into a new home.
So Rian is visually impaired, and as you can imagine, moving to a new space can be a massive challenge. To help him out, his sister Shalini did something absolutely brilliant. She used her knowledge of geometry to map his room. Taking a scale of 1 centimeter to 1 foot, she created this rectangular grid on a board. She used pins to mark the corners of the furniture and strung thick wool threads between them. This created a tactile map so Rian could actually feel the layout of the floor with his fingers. How cool is that?
Now, try to actively solve some spatial puzzles with me here. Looking at a setup like this, where exactly is the door? Well, if we know the coordinates of its edges, we can determine its exact width. Imagine the bathroom door swinging open on its hinge. Is it going to hit the wardrobe? A grid allows us to predict these real-world physical interactions before we ever lift a heavy piece of furniture. And that's why this matters. Grid-based thinking gives us total, confident command over our environment.
Section 2. The 2D Cartesian system. Now, let's strip away the physical room entirely to reveal the pure mathematical grid beneath it.
What's really fascinating about this comparison is how it perfectly illustrates that math is literally just the skeleton of our physical world. On the left side, we have the tangible walls and everyday objects of Rian's room. On the right, we've magically turned those walls into abstract, mathematical axes. We've transformed physical space into an infinite, measurable plane.
Let's quickly define the parts of this skeleton. Think of the x-axis as the bottom horizontal wall of Rian's room. This horizontal line in our two-dimensional coordinate system is simply used to mark distances moving side to side, so left or right.
Right alongside that, the y-axis acts exactly like the left vertical wall of Rian's bathroom. It's the vertical line intercepting our horizontal line, giving us our up and down measurements. And right where they cross, we have the origin, denoted by a capital letter O. It's our absolute starting point. It's essentially the exact bottom left corner where those two primary walls of our room map meet. At the origin, both our horizontal distance and vertical distance are zilch, 0. We write this mathematically as 0, 0.
Section 3. Understanding the 4 quadrants. Let's see how this builds when we break past the walls of the room entirely.
Because think about it, what happens if you walk backwards? Or what if you dig a basement? When we expand beyond the physical walls of our starting room and introduce negative numbers, our plane stretches out infinitely in all directions. The x and y axes now cross each other to divide this infinite 2D space into 4 separate, distinct areas. And we call these areas quadrants.
Notice how quadrant I is basically the physical reality of our room with purely positive measurements. If you move right and up, you are squarely in quadrant I. But look directly opposite to that, down into quadrant 3. If you move left of the origin, your x values become negative. If you move down from the origin, your y values become negative. In quadrant 3, absolutely all numbers become negative. We also have quadrants 2 and 4, which mix and match those positive and negative directions.
So here is the crucial takeaway. When we write a coordinate, mathematically, as p followed by an x and y in parentheses, we aren't doing anything mysterious. We are simply giving someone precise walking directions from the origin to that specific spot. The x tells you exactly how far to walk horizontally, and the y tells you how far to walk vertically. That's it.
Section 4. Plotting points and distances. Now that we know how to accurately locate points using these walking directions, how do we calculate the exact distance between two objects if they aren't lined up perfectly straight with the walls?
Let's say we want to find the distance between point A and point D here.
We can't just count the grid squares because the line cuts right diagonally across them. But look at what we can do. We can form a right-angled triangle between these two abstract points on the grid.
By building that triangle, we systematically find that diagonal distance. Step 1. We measure the shift along the x-axis by subtracting our x-coordinates. Step 2. We measure the shift along the y-axis by subtracting our y-coordinates. And step 3, because we now know the lengths of those two straight sides, we simply apply the ancient Baudhāyana-Pythagoras Theorem, the classic a squared plus b squared equals c squared, to solve for the hypotenuse. It is such a beautifully simple solution to a complex spatial problem.
And this brings up a fascinating property of space. Does reflecting that triangle change the distance? No way. Even if you reflect that triangle across an axis and push it entirely into a negative quadrant, the physical length of the distance between the points remains completely unchanged. Negative coordinates just tell us where something is relative to the origin. They do not mean negative length. Distance is always absolute.
Section 5. History of Coordinate Geometry. Because, spoiler alert, coordinate geometry didn't just appear out of nowhere overnight. It is the breathtaking result of thousands of years of human ingenuity spanning the globe.
Tracing this timeline, we can really see the deep roots of grid-based thinking. Thousands of years ago, the Sindhu-Sarasvati civilization was actually constructing entire city streets on massive, precise north-south and east-west grids. Centuries later, around 800 CE, the mathematician Baudhāyana laid down deep geometric constructions which included the foundational theorem for calculating distance. Fast forward to 628 CE, and Brahmagupta formalizes the concept of zero and negative numbers. And honestly, without that, our four-quadrant system just wouldn't exist. This knowledge flowed across the world, influencing scholars everywhere, eventually reaching Europe where, in 1637, René Descartes formalized the 2D Cartesian plane exactly as we study it today. To wrap up our explainer today, I want to leave you with a bit of a provocative puzzle to think about. Consider that massive timeline of human thought we just walked through. Imagine if Brahmagupta had actually never formalized negative numbers. What would our system of coordinates look like? Well, we would be completely trapped in quadrant 1. We'd be entirely unable to describe anything behind us, below us, or outside our immediate positive view. Without negative numbers, could we actually navigate the oceans, map the stars, or understand the universe the way we do today? It's incredible to realize that just by inventing a way to express less than zero, mathematics unlock the entire infinite map of reality. Thanks so much for joining me for this explainer, and keep exploring the geometry around you.